See that violent shaking when your machine changes direction rapidly? That's your machine fighting against physics. Imagine you're riding a motorbike and are accelerating to get to 100 kilometers an hour when you encounter a 90-degree bend in the road. It's not possible to continue accelerating and you have to hit the brakes, and this causes a jerk in your motion. In the CNC world, we are using a trapezoidal motion profile in LinuxCNC, and we call this infinite jerk. So we want smoother motion, and we need to vary our motion profile to look more like an S-curve. So as we come up to that corner, we decelerate a little bit within the timing constraints and negotiate around the corner without falling over. So for a CNC motion planner, this is extremely difficult to achieve. But the good news is, as of this month, the LinuxCNC team released a patch to the 2.10 master branch that finally brings jerk limited motion to the table. Today, I'm going to walk you through exactly how to get it. We're going to clone the repo, compile a run-in-place version of LinuxCNC, and configure your ini files to banish that jerk forever. So we hope, anyway, there might be a little bit of testing required because this is not officially released. So let's have a look on a piece of paper at what a motion profile looks like. Normally, what happens in LinuxCNC, you've defined your max acceleration and you've got a start point here, let's just say it's 0, and you want to get to, if this is speed, velocity, and this is time, what we want to do is, say we're accelerating to a cut speed of, say, 2 meters per minute. So what we would see is we would go up here at a velocity and we increase speed at our velocity until we get to that 2 meters a minute, and then it will taper off until you stop it. And then it will come back exactly the same slope. So these are the points that cause jerk. And this jerk can limit your tuning ability on the maximum velocity that you run. You might want to run this at a faster speed, so you might want to cut at 3 meters a minute instead of 2 meters a minute, and you might want to accelerate a lot faster and then come across here and come down a lot faster. But what's happening is that you can't do that because the inertia in the machine will need to be accounted for. And what I've found is that it's this piece here, that where you've got a mill with a heavy table, and as you stop, maybe on homing, and as you stop, then the inertia overruns the motor's ability to decelerate, which requires the same amount of energy as it does to accelerate. So what we want to do is to make this is sort of an S-curve up to our running speed and then come back down and so on, so that we ramp up slowly and we come down slowly. And the important thing about this is we've got to make sure that we don't violate where we move up to these speeds. We've set a maximum velocity in the ini file, and that's what's been determined as being what your machine needs. So because we're varying velocities, we need to make sure that we don't violate any of these machine constraints in the operation. So this is the goal. We want to get from this simple trapezoidal motion to a slower curved motion. So your motors can't produce infinite force. So your machine protests and vibrates, and you get following errors as the machine fights against inertia, and ultimately you have to run slower to compensate. S-Curve or jerk limited acceleration smooths out those sharp corners. It ramps up the acceleration itself gently without violating machine constraints. And it's the difference between slamming on the brakes on your car versus easing to a stop. Less vibration mean we can actually tune our machines to run faster and more accurately. So the benefits of jerk limited motion include reduced vibration and wear. It minimizes mechanical stress and damage to the machine. Improved accuracy. It prevents overshooting and ringing artifacts in finished parts. Smoother contouring, essential for high-speed machining to maintain path accuracy. And ultimately then gentler handling. Ideal for fragile loads like preventing water from splashing in a container during movement, which might be useful in an industrial or factory environment. So back over on your Linux CNC machine, the first thing I want you to do is open a web browser and go to linuxcnc.org and find the document. So documents. Now we're going to be building master branch, so always make sure that you read the correct version of the instructions because things may have changed. And you go right down here to under customization and development, and you'll find developer information. So click on building Linux CNC to start with. The next thing is we can open a console window. Now, the instructions in the documents don't tell you this, but I like to make a development folder. Some people use dev here, but what I've found is that there's also a dev folder under the root folder, and that can mean that you get confused later on the track. So I go make guitar development, it's already there, and then go cd devel to get into my folder. And you can see that I had to install a driver for my Wi-Fi here, so that source code is already here. So then we need a couple of tools which may or may not be on your system already, but we can get them now. Sudo apt install build essential. That gets all the essential software build tools like GCC and Make that are used to actually build your environment. And we also need Git, which is the program which allow us to go out onto the website and grab the Linux CNC source. So I've already got that here. And now we can git clone https github.com Linux CNC Linux .git, and we'll put this into a folder Linux CNC -jerk test. Helps if I say git. So here the source code is being copied into our new folder, and we'll just wait for that to complete. So there we have that. Now we want to just make sure that we are using the master branch of Linux CNC because the repository includes many branches of the software, including LinuxCNC and 2.98, etc. LinuxCNC-jerk test, I made it. And now we can go git checkout master. The instructions have changed here a little bit, which is great because we leverage more value out of the Debian environment. So with full stop Debian, so the subdirectory under where we are, configure, and that's defined that, and then we should be able to get build dependencies. So just a little bit of housekeeping as I go here. Just remove a couple of unused programs, and we can go cd /source. This is the folder that has all the LinuxCNC source code. There's many folders under this, and we can type in autogen to configure the build environment. So that's done that. And now we can type in configure. With real time. This tells LinuxCNC that we want to configure this to use with real time and the use space environment. Now we'll just go through and check everything. Make sure there's not really any errors here. It shouldn't get some, but basically sometimes you'll get an error missing dependency. So it seems to be pretty clear. So up here it says next compile by typing make and sudo make set UID. So I can't make it any easier for you. Make. This will go through the make file and make every component and every part and every executable that is part of LinuxCNC. What I should have done, we'll do that again. I just did a make clean then to clean everything out. And what I should have said is make -J8. And this computer has 8 cores on it. So you might only have 4 cores on yours or 2 cores. My desktop has 20. So what this will do is tell make that it can split the jobs up amongst those processes, so it'll get it done faster. So now it's processing all the HAL compile files to create the man pages or the manual pages for it, all the documentation. So there we have it, and it says you now need to run sudo make set UID in order to run in place with access to hardware. So if we go sudo make so that's done. So that just sets all the various permissions in the system folders. And now, if we type LinuxCNC here, in this folder, we're still going to get the old version that's in place, version 2.97. Now, that's because we haven't told LinuxCNC to use this run in place. So the way we do that is we type a full stop and then we go back to the base folder, cd / cd ... which takes us back to our top folder. And now we could put a full stop and go there we go. The two dots there are important. So dot and space, then dot / src. It's not src, it's scripts. So full stop space dash / scripts / rip environment, which is a script in the scripts folder we want to run. And now if we type LinuxCNC, we now get version 2.10. And wouldn't you know it, isn't that fantastic? Here we have under sample configuration, sim, axis, you'll find axis millimeters S-Curve, which is the one that I always use metric in Australia, and the standard one be axis millimeters. So that's the one that you want to run. I've already copied it onto my into my configuration. So I'll just cancel out of this and we'll go to our configs folder under the home directory. I think at this stage I can probably do it from here. LinuxCNC, configs, axis, there's a 9-axis simulation, and there's also this one here. So I want to just look at the ini file here. And there's lots of comments in here that tells you what's going on. So it says planotype equals 0 or planotype equals 1 will enable it. So we'll just go down here. Planotype, select the acceleration profile shape. 0 gives you traditional trapezoidal. S-curve, so it's needs 0 or 1. 2 was an experimental thing that they're going to remove to be depreciated. So 0 or 1 here. And then some comments about how to use this. And it says the maximum rate of change of acceleration is the maximum linear jerk. The maximum rate of change of acceleration, which is millimeters per second cubed. Setting this to 0 disables S-curve planning, regardless of planar type. So when you get going, it's suggesting that you start with, there's some suggested settings, and this is, it can be changed at runtime, and I'll show you how to do that so that you can play around with this on the fly. Ini traj max jerk, yep. Default. So we'll just go down and then we'll find that on the joints, down in the joints, we start putting in max jerk. Now it says so we just need to set that to our defaults, and I think it said you've got to remember that things might break with this, and if you're running a big heavy machine, you want to take a lot of care with this. So what you should do is start at a basic speed and then ramp it up by just editing the ini file here. So and it's set at the joint level. No, it's not. It's set at the axis level. Maximum jerk for axis X is 1,000 and Y 1,000. Z, so you can have different values on each individual axis. Start with a lower max jerk equal 100 to 500. Jerk should typically be 10 to 100 times of your acceleration value, and gradually increase the jerk in steps of 2 to 3 times. Test with simple moves and observe the motor current and torque, vibration levels, any following errors, and surface finish quality. So if it's too low, motion becomes sluggish and cycle time increases. If it's too high, it approaches trapezoidal behavior and it loses that smoothness, which is what we're trying to get. And optimal is smooth motion without excessive deceleration. So test arcs, circular interpolation with G2 and G3, check complex 3D toolpaths, and verify axis jerk limits don't overstep the or don't constrain the trajectory jerk. A few other troubleshooting things. So that's all in there. So we can now go back here to LinuxCNC. We can open up I opened the wrong one, sorry. A bit more careful, this one. So we're talking about those ini values. We can go into machine and we can show the HAL configuration, and we go to pins, ini, default jerk, and we can set the values here, so you can override that to maybe say it's 1,000 now. Simple as that. Now, the other thing that we can do, if I just close that for now, is under show HAL configuration, sorry, HAL scope. So if we look at HAL scope, this is LinuxCNC's oscilloscope. So we can map these, you can monitor these things in real time, and you can click on, I think we've got 8 values we can, at different values here, you get, I've got 4,000 samples, 4 samples I can do. So this one here, I've got joint motor position feedback. So that's the feedback coming from the of exactly where you are on each axis for joint 0, and it's coming from the encoder being a feedback. So that should be actually true, exactly where we are. And this one here is the velocity command. So that's the velocity command, and there should be an acceleration command. So then you can roll tape and monitor that. I'm not going to do that because this monitor is just not big enough to give us a good view of this module. So, but you can have a play with that and read up on the docs and find out how to do it or how to use it. But I did play with it and I did find that I was seeing that nice S-curve smoothed environment. So the real proof will be getting onto a real machine. So there you go. Now, if we just close this again. Now, if you want to do an upgrade here, all you need to do is do a git pull and it'll get the latest code from LinuxCNC as of right now. So the code that we've got now is 10 or 15 minutes old, so, or half an hour old. So if we go git pull, open terminal here, and if I back in our source code folder, if we go git pull, it'll get any new modules, so it's up to date. And then to build it again, you just need to type that make again. Get the source folder and then type make, run your make command again. It knows everything is up to date here, so it doesn't do anything. So the good thing is that sometimes if only one file changes, then it may only just compile one file and let you get going. So and then you do the sudo make set UID. So once you close this folder, your run in place is deconstructed, so it's no longer hooked up. So you need to leave this folder open. I used to run in place on production machines, and I used to just leave this folder open, always start LinuxCNC from this folder, and then if I needed to, I'd close it and do something else. But then to run LinuxCNC again, I would we'll just do that. If I close that folder, open a new one, I'm getting the old version of the software. So there you have it, the bleeding edge of LinuxCNC 2.10. Remember, this is a master branch. It's experimental. It can break. It can smash your machine. So don't run this on a production job for a client just yet. But definitely get in there, test it, and report back on the forums. If you found this helpful, maybe check out my guide on real-time kernel tricks to get the best out of your system. So happy tuning and machining. I'll catch you in the next one.